everybody. My name is Kyle Jackson. Welcome to the Biological Engineering Podcast. Thanks for joining us today. Today I am joined with a renowned faculty in biological engineering, the father of biological engineering, Dr. Ron Sims.
At least at USU.
Yes. So, thanks for joining us today. This is kind of a new thing that we're starting. We're trying to interview all the faculty and get everyone's perspective on biological engineering and what we do here. So
Cool. Good. You're going to get 50-minute lectures if you're not careful.
There you go. There you go. I think what we'll do to start is we'll just kind of figure out kind of where the department has been and maybe bring us up to speed of where it is today. So, Dr. Sims, what inspired you to launch biological engineering at USU?
Okay, good question. Appreciate that. There was and is the need for a new discipline. Biological engineering represents a new discipline with more inclusivity and more comprehensiveness, something that's more inclusive and more comprehensive as a vision for the future. So what am I talking about? We're going to talk about three main thrusts. 1, public health. 2, environment. 3, industry. We're going to put those together in a department called biological engineering. Those three have existed relatively independent. There's been some interaction, but not in an organized fashion in terms of an educational platform to train people.
Right.
So the inspiration I had was we need to combine, synthesize, and integrate public health, environment, and industry into one academic unit.
And when was this that you had
Okay,
this
that's
vision?
a really good question. This all started in 1970.
Wow.
So what I'm going to do is say history created the circumstances
Yeah.
to which this department evolved out of. And so what I'm going to say is I wasn't coming up with an inspiration in 2010 to start this department, but this department started when I first got my Bachelor's of Science degree in biology, which was in 1970. And what I'm going to do is line that up with what happened to the nation, because in 1970, the United States Environmental Protection Agency was established under Republican President Richard Nixon. And so I was part of that, and I was also part of the first Earth Day, which was April 22nd, 1970. And that was in the New York Times. Millions of people around the world shared in this. And so I'm graduating with a BS degree, wondering what to do.
Right.
So caught up in the national push, history, I ended up applying to the School of Public Health at Chapel Hill, global public health. I thought, boy, this should be good because then it fits in with saving the world, which is what we were all going to do.
Perfect.
And we're still trying to do in 1970.
So that's what we're doing today still,
That's
right?
what we're doing. Okay, so today, following up on that, look at our problems in public health today. What are we worried about today? PFAS. Right?
Oh, yeah.
Polyfluorinated alkyl substances,
Yes.
right? We're worried about things like diseases. Cancer, of course. Tuberculosis is still 25% of the global population. TB.
Oh, really?
Yeah.
I didn't
so
know that.
Look at the environment. People are worried what's in their water. How about microplastics in their water? Look at the air we're breathing. People are worried about air contamination of their lungs. And soil. How about this? So getting crops where we put biosolids on the soil to grow crops. Now the biosolids have microplastics, so we got a problem. Look at industry today. Industry, we're worried about food. Where are we going to produce food? We're worried about energy. We're worried about the industries that extract energy and minerals from the ground. We're looking at medical issues today. So we're looking at those things today that we can go back from 1970 on, but the deal was in 1970, the nation Washington established the EPA, which became a kind of a model for the whole world. And so then when I went to Chapel Hill in 1972, the industry...
And this was a master's degree? Or?
Master's degree in global public health.
So
while I'm there getting my degree in global public health, the United States State Department called the Agency for International Development, the United Nations Industrial Development Organization. They funded a project where they asked me to be the director when I was 23 years old. No idea, but the department head said, Ron, I was waiting for my wife to graduate. And so I was just graduating. I was the student rep for the Department of Environmental Sciences and Engineering. And he said, hey, we have this administrative kind of thing if you'd like to get involved with. Because what had happened, they had a tenure track faculty member, brand new, who was going to be the director of this program called an International Program in Environmental Aspects of Industrial Development. How's that? 1972. But they told this faculty member that he couldn't do it because he had to get tenure. And administration was not part of getting tenure. So, oh yes, so there we are.
Oh,
yes.
There he is.
Yes,
yeah,
there we are.
Thank
this
you, Henry.
Is senior going into going into college at the University of Dayton. How about that? So my bachelor's degree was out of the University of Dayton in Ohio. I minored in chemistry, and then I stayed on for a summer to take a course in ecology from a faculty member there who became one of our deans at Utah State University, Jim McMahon. He was a herpetologist, a snake expert.
Wow.
He inspired me at Dayton to apply to the School of Public Health, Global Public Health at Chapel Hill. So then, at Chapel Hill.
Yeah.
When I graduated, that's me when I'm 23, and the department head says, hey, Mr.
Wow,
Sims.
nice mustache. I definitely had a mustache
Does
like
that
that.
look like
You see it in the
73?
picture.
You got
on
it,
the fourth
72,
floor.
73. So I said, sure.
I'm not quite like that, but
So then I became the director of this program. But what that did is expose me to industry. We had 23 senior industrialists from developing countries come to the School of Global Public Health, and they were taught by industry people. And then they were also taught by some traditional faculty members, with traditional PhD, but most of the instructors had industry experience.
So what was your role as a director?
Super good. So what I did, I was the gopher. I went around and met with all of the industries. I flew to 12, 15, 20 different industries in the Southeast United States, setting up tours so we could go to the industry, take a tour of the industry, finding out how that industry was dealing with environmental issues, air, water, soil.
Wow.
So that gave me exposure.
This is a huge opportunity for a graduate student.
I didn't need to be an expert. They said, how about just put this program together, invite speakers, and then you take these international people around. And so what I saw, there it is. That's the International Program in Environmental Aspects of Industrial Development. So think about that. International, we had 23 people from around the globe. Program environmental, and then industry. So now we're looking at how does industry develop around the world,
right.
And what is the environmental. So what I started learning was, hey, this is a really global issue of environment and industry, and I became fascinated with industry, learning from anywhere from steel to food to the electronic industries that were going at that time, industries developing fossil fuels, taking off like crazy, coal gasification. So I got exposed in a good way to what the world was struggling with.
So you've had a lot of inspiration over the years.
Then, exactly. Right. So then from there, when I'm getting ready to graduate and going, now what am I going to do? One of my committee members said, hey, there's a job. Oh, by the way, we graduated at the United Nations. So we took all 23 people. I was at the United Nations. The head of the Department of Environmental Sciences and Engineering, Dr. Dan Oken, who came down from Harvard. He got his PhD at Harvard when I was born.
Oh, wow.
In 1948. So we graduated. He was there. I was the director. I sat in the audience. He was the dean. He was the department head of Environmental Sciences and Engineering. And anyways, the whole class got certificates at the United Nations as a result of this IP program. So I'm getting more and more, interested in these global issues. And then when I graduated, they said, Ron, you need more industry experience now. So one of my faculty members told me about a job in South Carolina that was working at Bayer, the German company, Bayer Aspirin. And so, I said, hey, I applied, and the advertisement said you need 5 years of experience. And I had 2 years of IPAID and then my master's, but I applied anyways and I got the job.
Nice.
So there were 3 or 4 candidates. Anyways, I ended up with a job, and that job was the supervisor of the Environmental Control Laboratory for Bayer that just opened up a new plant in Charleston, South Carolina.
Mm-hmm.
They're situated on a river that goes into the estuaries. So here we are, and what do they make? They make textiles, toxic chemicals, the stuff that does this, that dyes our clothes.
Yeah.
They're dangerous compounds. Where's this stuff going? Into the estuary. What's in the estuary? Seafood.
Oh.
Fish. So now I'm in charge of the Environmental Control Laboratory, and the state is really looking carefully. Of course, this new industry is bringing in money. But yes, there it is. That's Bayer. That's Charleston, South Carolina. Yeah, so these are quinones. These are things, what dyes your shirts are benzene rings and then modifications of benzene rings. What turns out is these chemicals are really close to medicine, to what they describe for medical products. And so in studying these chemicals, we had to learn a little bit about the chemistry, aromatic, aliphatic chemicals, so that we could degrade. So this, that was with IPAID. So that's the international program. That's some of the industries that we had participating in the IPAID program. Is we had to treat the waste biologically, but we also, because the regulations weren't out yet from the federal government, EPA, on what they were going to regulate, then I was also running activated carbon and reverse osmosis, and we were doing UV lights, and we were doing abiotic treatment. And then we were doing biotic treatment. So that's where I got experience doing upstream as well as downstream processing, testing it on these toxic, carcinogenic water. One day the wastewater would be green, the next day it would be yellow, and then it would be blue. But we put it into, so Bayer was very good about that. They put it into lagoons, and then we treat it in the lagoons. And so I learned a lot about biological and physical chemical wastewater treatment at Bayer, and I spent 2.5 years there, and then they said, I said, you know what, I need to go back and get a degree in engineering, because I know a lot about the chemistry, the biology. My master's in global public health was in chemistry, biology. Mm-hmm. But after working out here, I went, I can study the chemistry, biology, but I don't know how to design the size of these reactors.
Right.
And how long it takes the water to get treated. So I said, I'm going back and get another master's in environmental engineering. And so the plant manager called me in and said, you sure you want to do this? You know, you're making money, you're moving up. How many years are you going to get a master's? I said 2. He said, do you realize how much money you're giving up in that? And by the time you get that, if you stayed here, and I said, you know, I want to go back to school. So I quit that job, and we moved to Washington State University, the third one, because my wife, Judy, had applied there, but then she decided to go to Chapel Hill, where I met her.
Wow.
So when I was saying, let's go, we're young, we don't have kids, we can move, we said, how about Washington State, where she applied? And they had an environmental engineering program, so we applied out there, got accepted, and took off to Washington State.
What do you say, serendipity?
Serendipity.
Like it was meant to be?
It's a big part of my life. Taking risks and serendipity.
Yeah,
huge.
Sure.
That kind of outlines the way, I mean, exploring kind of thing, but not getting, I've never been a real big one when somebody says, what's your 5-year plan? I go, I don't know. And sometimes they don't like that. So what I do, but I like it. I'm good with that, because I find it much more adventurous to explore than to set out on a concrete kind of schedule where I need to be at this place.
Right, yeah.
And you know why? I'm a first-generation student. My parents never went to college. They didn't have any expectations of by this age you should be. They just said, you're going to college? This is great. Go to college. And so I thought college was going to be military school. I thought, well, that's okay, too. I didn't have a problem with that. But I had no idea what the heck. None of my aunts, uncles, nobody went to college. So when I go to college, we didn't have Google. We didn't have any cell phones.
You had to go to the library.
We didn't have any of this stuff.
Tuition wasn't crazy expensive.
Yeah.
That's right. So the idea of serendipity, let's go to Washington. I was in a learning mode. Let me pick up more skills here. Plus, I'm learning more about industry, environment, and how to deal with some of these problems. So at Washington State, that was around 75, 76. I got a master's, and that's what we're looking at there. That one you just had, right there, that's the Dvorak National Fish Hatchery, which is the largest steelhead trout hatchery in the world.
No way.
It's on the upper
That's so cool.
Clearwater River in Idaho. How's that? And so the department had a project there that I ended up doing my master's where they were growing fish. They teamed up. Here's something. The civil engineers teamed up with the fisheries people so that they could keep the water slightly warmer, and that would increase the population of fish, the productivity of the fish,
Oh, okay.
that they could then use to stock lakes and things like
Yeah.
that. And so they teamed up together, and what the engineers had said is, wait a minute, they had all these people feeding the fish by hand. They go out and distribute the fish in these big raceways,
Right.
and they have hundreds of thousands of fish. So the engineer said, we've got it. We'll set up a pipe, and what we'll do is we'll put a building and all the food in this building, and then we'll put sensors, light sensors, so we can, in the raceways, and we can detect the fish and how many and how much, and then we can proportion the food. You don't need to hire 50 people to go.
Oh, okay.
So they did that. And
Wow.
then what happened at this site?
Like an automatic feeding.
Yes, automatic feeding. Well, you know what happens with sound through water. So, of course, when the motor went on to feed the fish, all the fish heard through the water, and then they all ran to the pipe where the food came out. Well, that was cool, but then you had 20,000 fish scraping the sides of the fish as they all got together, kind of pushing each other, elbowing. Fish don't have elbows, but that kind of thing. Pushing each other, scraping the sides of the. So then what happens? The fish start to get disease. And oh man, they put $1 million
Right.
way back in 1975 into it, but then the fish started to get disease. So they said, okay, we're going to add antibiotics to the water to make the fish clean, but then to make the fish healthy. But then the antibiotics got in the fish, and so you can't release the fish with antibiotics. 'Cause
Right.
You can't eat them. So they had some other scientists, fisheries biologists, say, hey, you know what? We're doing studies with the fish, and if you add more potassium and magnesium and calcium, the fish
the
can
food?
Yes, they don't get sick as fast. Plus, the fish were excreting ammonia in this recycle
Right.
system, which is what they do best. And they said, hey, if you add some salts, the fish can tolerate higher levels of ammonia. So this was an experiment between the civil engineers and the fisheries biologists on a new experiment to try to grow these fish faster and better. What happened then is when they added these salts, the fish were better, but then when they let them out, they didn't know where to go because they thought they were in the ocean. And these fish were
Oh.
supposed to go back down to the ocean. But they didn't want to leave because they said, hey, I'm in salt water now. I'm good.
Yeah.
So you know what they had to do? They had to put the fish in trucks and take the trucks with the fish down to the ocean. And then they release them and they tag them. And then,
yeah.
they'd wait for the season for the fish to come back up. Well, what
Yeah.
happened is this dam is one of the tallest dams in the world. It's huge. So the fish couldn't get up this without fish
Yeah,
ladders.
poor farm fish.
Fish ladder. So the fish ladder that they built was like a mile long, half a mile long. But what happened then is when the fish started back up the fish ladders, the birds started eating the fish because they could see them from the air and come down and pick up the fish. And so the predation on the fish by the birds was so much that they said, this isn't going to work anymore. We're losing half of our fish. So you know what they had to do? They had to go to the ocean and put the fish in trucks and bring the fish back up to the hatchery. So somebody then said, if we keep doing this, the fish are going to forget how to swim.
Yeah, they're going to be expected to be driven everywhere.
So we're going into that now. So at the end of this whole master's degree, they quit. The civil engineers backed off and said sorry, and the fisheries people said no, we're going to go back and do our thing and feed them, by lots of people, and we won't have this recycle system because it screws up their whole system. The temperature increases and they excrete more ammonia, so they went back to where they were, and that was my 2 years there. Then
Okay.
what happened after I finished that, I had an advisor call me, back up just 1 year. You were good. Let's see, maybe one more. Where that was, there, right there. That's Research Triangle Institute at Research Triangle Park. So I had an advisor, because I was looking now, would I go for PhD or what do I do now? And an advisor called and said, hey, coal gasification. By the way, 75, 76. During that time, we have RCRA, Research Conservation Recovery Act. And that RCRA was passed by Congress to say you have to take care of waste. We're growing our industry in the country so much that we now have to pay attention to what happens to the waste. We have to dispose of it correctly. And so RTI, Research Triangle Institute, back to North Carolina, back to Research Park. And what they were doing, I was working with the chemical engineers there because they needed somebody who had a background in civil and in biology to start looking at the toxic effects of coal gasification. So they were taking coal, which has high sulfur in the eastern part of the country, and they were converting this coal into gas. So it's called coal gasification. And this is when we had the energy crisis. U.S. had OPEC, was pulling back the energy. And so there was an energy crisis, and the Department of Energy, what was at that time, gave RTI a couple of $1 million to look at taking coal and changing it into clean gas.
Wow.
So I got involved then to work with the chemical engineering department, but providing biology and kind of civil engineering. Anyways, got really interested in the carcinogens coming out of
So
coal.
wait, you were working on the gas, or you were working on the
Yeah.
coal?
So it was gas. So what they did is the engineers took the coal.
Or, I mean the solid.
Yeah, I was working on the gas phase.
Working on the gas.
Because what they had to do is clean up the
Yeah.
gas. So you take the coal, you make gas, but then this gas not only has methane, but it has sulfur and it has all these additional metals in there.
Yeah.
It has other organics because it's incomplete combustion, right? You're not burning it to CO2. You want to save that gas with energy. So what you do is you quench it, you rinse it with water, and that will rinse the pollutants
Oh.
out, and the methane goes
like
through.
steam, or just like a hose?
Yeah, so
Water.
they use both water and increased temperature. But what happened? The steam and the water ended up with all the pollutants in the water.
Right.
So now what you've done is a phase transfer. You now have clean gas, but you have this water that's highly carcinogenic.
What would you want it to be?
So that became
solid
my
as
PhD
well?
program.
Oh,
Is looking at this.
that was your whole PhD.
Yeah, was
Amazing.
taking care of the carcinogens that come out of this, and then trying to find a way to apply the carcinogens to land, where you actually applied at a rate and amount so that the microbes in the soil could eat up the carcinogens.
Oh, cool.
Yes. So moving on here, RTI. So I spent a couple years there, and that's where I got inspired to go back for my PhD. So now we're right before that, we're going to NC State. I worked for a chemical engineer. I found a chem engineer who was really interested in what I was doing at RTI.
After your PhD, you worked.
This is for my PhD.
Oh, this is again for
Yeah,
you.
so I said, okay, I need now. Can I put this all together from RTI? I said, now I'm ready for a PhD, and so I started looking at how you can combine industry and academics, and I found a chemical engineer at North Carolina State interested in coal gasification, and we decided to design a land treatment system, a treatment system for the waste coming out of coal gasification plants, so that we would use the soil to assimilate, not to accumulate, by using microbes to break down the chemicals, and also for metals to apply it at a rate that would be low enough, using enough property, so that you wouldn't accumulate metals in the soil.
How did you find this chemical engineer? Because there wasn't.
So I started, good question. So Rock, we have North Carolina State, and we have Duke, and then we have UNC Chapel Hill. And UNC Chapel Hill, they didn't have chemical engineering. They had global public health. And then North Carolina State had the strongest chemical engineering department around. So I started asking around, and I looked at civil, and I looked at chemical, and I found a guy who was in the agricultural and biological engineering department. How's that? So it was
There you
BAE,
go.
Biological and Agriculture Department. He was a chemical engineer with a joint appointment, and he was interested in environmental work. And he didn't know much about environmental biology, but he wanted that kind of a student. So I went and interviewed with him. Meaning other people said, he's a tough one. He had one graduate student make it in 10 years, and that was me. So he was pretty rough, meaning he was a genius. He was a Rhodes Scholar. And so when I went to see him, he threw a math book across the table at me when I went to interview him, and he said, you need to minor in mathematics, and you need to take a course in math beyond which you'll ever use if you're going to be my student. And so
Sounds
I went,
awesome.
oh boy, here we go. So that's a challenge. How's that for going, hey, serendipity, fail forward kind of thing? So other students said, don't take him, he's really tough. It's Michael Overcash. And I decided, okay, here's a challenge. I'm going to take this guy on. So So I did, and I said, okay, we're gonna, tumble together. We're gonna do a rough and tumble together. So what ended up is he and I worked together. He was genius. I learned from him so much. I used to study the way he approached his logic and engineering kind of thing. So I learned a lot of chemical engineer under this guy. And I had worked at RTI in the chemical engineering department because what they needed was somebody, they were chemical engineers, need somebody in the life sciences. So then my PhD became biological engineering, but mixture of industry and chemical engineering. So I ended up minoring in math, minoring in environmental toxicology, minoring in soil science. And what happened is I ended up spending 3 years. And he said, Ron, you only need 2 years. And I said, are you kidding? This is my last shot at this. So I want to get as much as I can. So if you'll support me, I'm going to do 3 years instead of 2 years. So I ended up spending 3 years. Now, as you can see, now I've got this environmental, public health, industry, EPA, IPAID, United Nations, State Department, this mixture looking for a place to go. And then we go to Utah State. So I'm looking for a place to put this. By the way, in the meantime, my wife, I met her at Chapel Hill, and she got her master's with me a year behind in public health. And then when I went to Washington State, she got a second master. She got her second master's at NC State, North Carolina State, in soils, in designing septic tanks. Yes, she is in charge of the state of Utah's on-site wastewater treatment training center. So she trains people on how to design and install and monitor and operate. And we took classes together at Chapel Hill.
Wow.
And then what happened at NC State, she majored in soils and minored in engineering, civil engineering. And I majored in engineering and minored in soils.
Cool.
So we ended up, we do a lot of tech talk together. So that's Judy. And so we decided, okay, NC State. In fact, she was working for an all-woman consulting firm in North Carolina. And when I finished up my PhD there, I was going to work at RTI, Research Triangle Institute, with a joint appointment at NC State. She had a job with an all-woman consulting firm. And we came out here to interview because they were looking for somebody in environmental engineering. But on the way out, they said I could come out. And I brought her with me, and they were coming up to Logan, and we go, this isn't fair. We should go up and tell them we're not interested. What are we doing? We bought a house in North Carolina. I had a job in North Carolina. She had a job in North Carolina.
Right.
What are we doing? What are we doing here? So we decided that we weren't being honest. So he said, when we get up there, we're going to say thank you, but we're going to pay you back. We're really not interested. Well, dang it, we're driving up, and things really look pretty. And we're going, geez, this place is really nice. So the more we get into Logan, we go, maybe we'll just go through the interview and see if we want to come here, but we won't. And after 3 days here, we said, would we really, if they offered a job, quit the job back there, sell the house and come out here? Would we do that? So we talked about it on the plane on the way back. But what happened was all the faculty members and all the students were so nice here. They were so good. They were real people, right? The faculty were not real distant, from you. They were real people. And
What
so,
year was this? Like,
what's
when
that?
did you move out here? What year?
1982. Yeah. So we came out in 1982 and interviewed, and we ended up falling in love with the place and really liked the people, liked the faculty in civil environmental. Joe Middlebrooks was the dean at that time. So we were going back on the plane saying, wow, would we really do this if offered the job? So we kept talking about it, and we got back and we got a call. I got a call a week later saying, okay, we're going to offer you the job if you want it. And then it really came down. The crisis came down to what do we do? So we made the decision, okay, we're going to quit. We're going to Utah State. We are going to quit. And everybody around us, all our friends, were shocked. Like, what are you doing? You have a house. You have 2 jobs. She has a job. You have the beach. What are you doing going to Utah? So anyways, we said, okay, we're risk takers again. We're going to take off and go to Utah. So that's where I came here in 82 in civil and environmental. So the deal was, after a number of experiences, we had a new dean come in, and it was Scott Hinton. Mm-hmm. And he came in, he was electrical engineering, and he said, what is this Department of Biological and Irrigation Engineering that's so small? Well, biological and irrigation engineering was, that title was given by Win Walker in 1992. He became the head of that department. This department started out as agricultural engineering. How about that?
Right.
Long ago, it was agricultural engineering, and then the deal was he incorporated that. I'm just looking at the notes I had here. In 1914 is what I was going back. USU created a new school called the School of Agricultural Engineering. And then in 1947, the Department of Agriculture and Irrigation Engineering was formed. 1947, the year before I was born. Then we had famous people. The irrigation program, I even knew that when I was at Chapel Hill, school there, because Chapel Hill had an international program called International Program in Sanitary Engineering Design, while I was the director of IPSED. But out here at Utah State, they had a worldwide reputation for irrigation engineering, and we knew about that. So the two programs in the country that were the strongest was Utah State's agricultural engineering, and then Chapel Hill's IPSED program. So we knew about that long ago. And famous people out here included Lyman Willardson and Bob Hill. Robert Hill was here. Don Griffin, Bud DeLay, Dean Peterson, who the building's named after, Peterson Building.
Oh, okay.
He was in there, and Win Walker. And so most of these guys were all civil engineers, but they had so much going on in irrigation, they formed their own department.
Cool.
So Win Walker became the head of that department about 1982, whenever I came to Utah State. And then he changed the name of that department because biological was getting bigger and bigger, and he changed the name 10 years later in 92 to biological and irrigation engineering. So we're up to 92.
Almost in the home stretch, I'm feeling.
Almost in the home stretch. You got it. So Scott Hinton comes along in 2002, the new dean, right?
Yeah.
And the new dean calls me into the office and he said, "You have your PhD in biological engineering?" And I said, "Yeah." And he said, he's an electrical engineer. And I was on the search committee to vote him in, he was terrific. He had patents. He came out of AT&T Bell Labs. So he says, "You have an industry background," and he has an industry background. He said, he likes to make products. He said, industry. And he said, I've been he was in AT&T Bell Labs in photonic switching. And he said, biological engineering could be something like electrical, where you have components and devices and parts. He had capacitors and resistors. And so I said to him, "How about and he asked me, could I introduce him to some biology? So I showed him what was going on in synthetic biology. I said, this is a new area. And I thought that would connect really well because parts and pieces of DNA would connect with what he's thinking about electrical. So he became he was the idea of thinking about why don't we grow the department, because he saw biological engineering as the new, what was electrical and chips from when he was at AT&T Bell Lab. And I said to him, "Hey, this is like changing jobs without moving." But I was director of the water lab at that time, the Utah Water Research Laboratory.
Right.
So I was a director there for about 7 years.
Right,
I love
the
my
water
job
lab.
there. I was on the river. Yes, that's exactly it. I was on the river. Judy worked down there. That's when we were in civil and environmental engineering. I was the head of the environmental engineering division for a while, and then I moved from there into being director of the Utah Water Research Laboratory for 7 years. And that gave me another chance. I was teaming up with American Petroleum Institute, the Electric Power Research Institute. We had $1 million contracts with them looking at trying to deal with environmental issues that they had. Anyways, then Scott said, "That means you'd have to leave the director's position at the water lab and come up here." And he said to me, "It looks from your history that you're a risk taker." And I said, "You got it, exactly. I am a risk taker." He said, "Well, if you want to do this, I'll let you stay on everything, all the committees, whatever you want to do. I won't pull your students away. But would you help me to generate a brand new department?" Well, at that time, the president that came in was Kermit Hall. Kermit Hall came in.
What
right
year
before,
was this?
This is, Kermit Hall. So Scott came in about 2002. Scott came in 2000, but he came in, Kermit Hall came like 2 years or a year before that. And Kermit Hall just asked all the deans to resign. He came from North Carolina. He was at Chapel Hill. He was the provost of the North Carolina system of education. So he came out here and he asked all the deans to resign, and then we started looking for a new dean, and that's where we came up with Scott Hinton in 2002. And Scott Hinton was an electrical engineer, but he called me in and he said, "Hey, biological engineering looks like the way to go." And I said, "Hey, if you're willing to do it." Well, Scott Hinton, our dean, was assigned to be the chair of looking for the new provost, who was Ray Coward. So now what happened is we had president lined up, the provost lined up, and the dean. And the dean initiated the idea of starting a biological engineering department and had the provost support and then had the president's support. And so I worked with Scott to write out
Cool.
the biological engineering department outline, which we got approved by the Board of Trustees in 2010.
Cool.
I've made a pitch to the Board of Trustees. Where this all comes from, as you said, as we come back around, is this whole history gives me, talking about launching the BE department, goes back to public health, environment, industry. But those have been relatively separate, some together, but the BE department is the integration of these three separate pillars
Mm-hmm.
so that we can try to integrate the interactions between public health and environment and industry. So the idea then is to grow all three of them to improve public health, improve environment, improve industry. And engineers, what are we supposed to do? We're supposed to create new things. Einstein said engineers create things that have never been.
Mm.
So the idea of having a biological engineering department where you can create new things that improve public health and environment and industry together is the vision. But see, that vision
Cool.
didn't come out of me just waking up one morning in bed and going,
No.
we need a new department.
It's
that
been
came
your
from
whole career.
the whole career.
Yeah.
Yeah. So founding the
that in
biological
your
engineering
head.
department is the culmination.
Wow.
I'm happy of a whole career, right? So that was formed in 2010. And then in 2014, I had been working with the dean since 2006, something like that, for the transition. I came in as the interim department head of biological and irrigation. My challenge on that one was to talk to the irrigation engineers and ask them if they could move to civil. And since most
Yeah.
of them were all trained to civil, this wasn't too big of a deal.
Mhm.
There wasn't any resistance. We got along well. But then we moved. The idea was they went to civil, and then we continued to add faculty in biological engineering. And so we did
Ah.
that while we were getting ready for the department to be approved. And then in 2010, we had official
So
approval.
how long was it BIE?
It was 1992
To-
to 2010. So it was a long time. It was, but we were going through the transition almost for the last 10
Yeah.
years when the dean came in and wanted to shake things up and saw this opportunity. So you know what? Serendipity again. He comes from industry. I come from industry. He comes from electrical. I come from these different parts, and we get together and we go, we need to get industry innovated into this dang department. And so the idea then is to support industry and make products. So then that influences, improves the environment, and improves public health. And so in 2014, I went, you don't want to stay on forever. You start to think, okay, I want to be here forever. But the idea is get out, make your contribution, move on.
I like
So
that.
then I decided to get into this SWBEC, Sustainable Waste-to-Bioproducts Engineering
Yeah.
Center, start that and continue that, but then support the growth of the department and whoever else wanted to take that over. Because we
Cool.
had the infrastructure now. So that's how this department came. That's
Amazing.
the long story. It is.
Amazing.
It is. You talk about, serendipity and all kinds of things put together, and then looking for the moment to take advantage of that. And
Oh,
the dean
yeah.
walks in and says, "Do you want to start a new department?" And
You got to take risks. That's
gotta
the
take
whole
risks.
moral of the story, I think.
got to take risks, right?
Yeah.
Right. So my advice to students is, yes, take risks and fail forward.
Yeah.
Take risks. You're going to fail. So take risks and fail forward. Get yourself back up and get going. But don't. It's such a shame, as you go through your career to say, well, I wish I'd have done that, but, I really. And see, when I didn't have anything, when I grew up in the ghetto and nobody went to college, what did I have to lose? So this was actually good because, okay, try it out. And if you fall down, get up again and go again. Because
Yeah.
nobody above you, no uncle or aunt or parents are going to yell like that. You just have a lot of freedom. So you have the freedom. I call it the freedom to fail. So there's two types of freedoms. One's freedom from persecution, which we talk about, but we don't talk about freedom forward. We don't talk about that much. And what education gives you, since I'm the first in my family to go to college, education gives you the freedom to move forward. And you can take that either by, there you go. So that's my great-grandmother on the left, Agnes, and my mother in the middle, Rita, and my
Awesome.
grandmother on the right, Stella, and then my sister in the front. And this is actually where we live, folks. This was in Pittsburgh, Pennsylvania. if you can see, there's a gas station right there, and there's my neighborhood. We didn't have a tree. We had one tree in the backyard. We had most of our soil had glass in it. We lived in where we walked out. There was probably 3 feet. There was a sidewalk to the highway, and so I grew up in you might say an urban.
I didn't know that. I didn't know that.
Urban environment. Yeah. So that's where I started, and where we lived in Pittsburgh, and then we moved to the suburbs for just 5 years, and then we moved back to the city because we liked the city, a different part of the city.
You
I'm a
moved
city
back
guy.
to the city.
We did. I'm
Hold
a
on,
city guy.
that doesn't make sense in my head.
No.
Growing up in Logan,
And then we're in Logan.
Yeah.
You know what was interesting? Judy grew up on a farm. See that car? So that car, when I was an undergraduate, that he just had there, that car is what I sat in when I was an undergrad in Dayton, Ohio. The teacher who taught biology said, I need some undergrad volunteers to breathe carbon monoxide. He had actually a grant from the National Institutes of Health. He had a grant where they were looking for the scenario was this.
To get kids to do it.
Yeah, in the 60s, people drove through cities. America's growing, and they don't have air conditioning, and so they wind down their window, and they're driving through cities, and the tailpipe of the car in front of them has all this carbon monoxide. And so as they go from block to block, he got funded because then as you breathe carbon monoxide, your reflexes go down, and maybe your tendency to get in accidents. So he got funded, and he walks in and he said, I need volunteers to sit in that car every Saturday for a semester and breathe carbon monoxide. And what he's going to do is have a chemist who makes a carbon monoxide generator. We're going to sit there. And first, before we sit in the car, there were 8 of us. Before we sit in the car, he's going to prick your finger and take a hematocrit, right? And then you're going to go sit in the car for a couple hours. And then you're going to come back out. And not only the hematocrit, but we did a whack-a-mole in those days. Light would go on and you had to hit to turn the light on.
Oh, okay.
Then we come back out afterwards
That's
and
cool.
they prick your finger again and then hit the whack-a-mole again. And I did that for a whole semester. But anyways, I sat in the car, breathed carbon monoxide, and then trying to get involved in what you guys do, so many opportunities in lab. Well, and he actually got it published. It's a refereed publication. That's we're going to talk about that a little, what he's got up there a little bit later.
Oh, good for him.
So the deal was so we're in lab for physiology. I took pre-med courses. And then I took the one in environmental but got inspired because of Earth Day. But in physiology lab, we were looking at glucose metabolism. I ate a cup of sugar. And then what they did is they put a tube up my nose and down my belly. And then every 15-minute, 3-hour lab, every 15 minutes they sucked out juice. And they measured the glucose and some other things going. And after an hour of this, where I drank the sugar, ate the sugar, we started to see red stuff.
Were you paid for this one?
No. This is all volunteer again. And what the teacher said is, I think we're pulling the lining of your stomach out now, so we probably should stop.
Oh.
I remember that. So what was happening is they were pulling tissue out. It was kind of red, and there was belly stuff.
Okay, because you don't feel that, right?
I didn't feel it at all.
Yeah.
So we stopped. They pulled it out, and that was my volunteer in physiology lab. See, I would do anything.
That's kind of awesome, though. It wouldn't fly today, but
Can you imagine sitting in the car and breathing? If I said, would you guys mind breathing some carbon monoxide for a couple hours? Then I'll take your hematocrit. Or how about put this tube down your belly? I want to suck out some stuff and just see what happens to your belly. Anyways, those are the type of things I did in order to get involved in some activity within classes. So the BE department comes out of all of this. It's I'd say a culmination of a career.
Super awesome. You mentioned SWBEC.
Yes.
Could you explain SWBEC in a way that maybe a non-scientist could understand?
Yeah. So how about this? Sustainable Waste to Bioproducts Engineering Center. Sustainable refers both to waste and products. So sustainable waste, we're always going to have waste. And in fact, we can't get away from it. Industry, and that's a new building that they built for me that's shown on the screen there. That's the Algae Processing and Products Facility, which is part of the Sustainable Waste to Bioproducts Engineering Center. So what I'm doing is I go look.
I haven't been out there yet. I'd love to see
We should
it.
give you a tour.
Yeah.
They just built it. It's 2 years old.
Yeah, it's
and it was put up for me 2 years ago. And what we do in that facility, is we grow algae on waste. on what people consider waste. So I look for industry waste, and then I try to see if we can grow algae strains on it. And then out of that algae, we make products. So we make biodiesel, bio oil, bioplastics, biofertilizer. So what we're trying to do is called upcycling. So we're taking, not just recycle it as a waste, but upcycle it to make it more value. So the idea here is supporting industry. See those shoes there? Oh, well, anyways.
Shoes, Henry. Come on. Just kidding. Just kidding.
Okay, it's okay. Sorry. Anyways, we
shoes right there, the green ones. Yeah, yeah.
There, that's oil.
Oh, okay.
See the oil?
We're
That's
not getting
bio
shoes.
oil.
That's bio
There.
oil.
So that's bio oil, where we take the algae and
Technical
cook it.
difficulties.
We do
Wasn't
the same
Henry's
thing
fault.
that the dinosaurs. So the same way. And there's
There's
the
the
shoes. Yeah, shoes made of algae.
Oh, what? Who
How's
made
that?
those?
We send it to Algix. It's a company in Mississippi. And we send the algae to Algix,
awesome.
and Algix comes back with things like...
Oh, they just...
They sell these. You can sell them. I don't know what they charge now, but sell now. So what is that? So what happened then is, we'll talk about this, but the biofilm photosynthesis. When the sun hits the photosynthesis increases the pH of the system, and by increasing the pH, it precipitates out. See, that looks like that crystal in
Really,
there?
it metabolizes and increases the pH, because I thought it would decrease.
Yeah, it removes
right?
CO2, so it takes out carbonic acid.
Oh,
And
it's
then the
it's a
shift is
plant.
Bicarbonate. and
Oh,
carbonate.
yeah.
So tech talk here, it actually ends up increasing the pH that precipitates, and that's a slow release fertilizer. So now we have taken a waste and made a fertilizer
That's
out
awesome.
of it. Yeah, and we actually pH. All right, amount of
Yeah,
acid.
what is a pH, Dr. Sims?
There you go. Okay. Amount of acid or base. So what photosynthesis will do, they'll increase the base proportion that's in the water, the basic proportion, like lye soap. All right, if you got lye soap or something that increases pH, so it's not acidic. It's not going to be like drinking fruit juice that's acid. But this is going to be in the opposite direction. When you increase the pH of the water, which means you take away the protons, you end up precipitating this chemical, which turns out to be a fertilizer.
And usually the carbon dioxide, when it dissolved in water, would decrease.
Carbonic acid, right?
And
that's what plants use, so they suck it out.
So plants actually suck out the CO2, so the pH goes up.
Yep.
Acidified the ocean, right?
How's that?
I think we changed the pH
Oh,
of
have
the
we?
whole ocean.
Yeah.
By how much?
Like
Could.
1 or something.
Yeah.
But that's
In
like
what direction?
It's a logarithmic scale. More acidic, because we're
Because
pumping out all that CO2 into the environment, and that's where it all goes.
Fascinating.
Yeah, so in this case, it raises pH so much that the stuff precipitates. So we get a fertilizer out of the waste. So this is called upcycling. So SWBEC, we look at taking waste and upcycling into products.
Wonderful.
That protect the environment and protect public health, but also support the industry. See, engineers today should be taught it's no longer the environment versus industry. That's an old paradigm. That's no good.
Yeah.
What we need to do is embrace the fact that we're engineers. We're taught to be creative. Einstein says engineers create things that have never been. So to do that, we need to get our heads together and learn about the tools. That's why you take thermodynamics and kinetics, et cetera, mass transport, so that you can say, how can we put these tools together that will enhance industry and the environment and public health all at the same time? And that's our challenge. That's what we're training people to do. We don't have the answers, but we have a new discipline. And that discipline, as we say, is more inclusive, more comprehensive. That's how we started this. The new discipline is more inclusive and more comprehensive, with the idea of having a new vision for the future, which is to embrace public health, environment, and industry, and make them all go up together.
Can you talk more about your premise there, like the shift between industry and environment and the conflict that was there in that paradigm, and how, like, I think your time at Bayer really was like they were involved in trying to clean up their waste before like the EPA was even interested in it.
Yeah.
Whereas I think like some companies maybe weren't as environmentally friendly.
Yeah.
And now like I think today there still is a bit of that paradigm, and that people think that industry and environment can't get along.
You bet. You bet. Excellent.
It sounds like you're proposing that today we actually need a new paradigm of industry is responsible for the environment.
Yes. New paradigm, like you say, that's the new vision, is to say, okay, and you know what, when you talk to industry, if you, in terms of industry language, if you say, okay, industry, when I worked at Bayer in the environmental group, they considered it throwing money down the drain. But literally, that is, we're throwing money down there. We have to do these regulations. But then they turn around later and they go, hey, if we can make a product out of this, if we can make money, if we can make a product, we get good PR, we get money, and then we can advertise ourselves as pro-public health and pro-environment. And so industry starts to get a bigger idea of their role and a bigger way that they can make a positive impact. Industry traditionally would hang out. They wouldn't put up a sign. They didn't want it. Any publicity is bad publicity. Well, turning that around to be good neighbors, and with all the modern media methods of chasing industry and following, the idea of industry's in the process of turning around and inventing themselves as good neighbors. And part of that good neighbors is we tell them, you can make a product out of this, you can upcycle this, you can make money out of this, you can get good PR because you're actually show ways you're improving public health, show ways you're protecting the environment. Now they're starting to talk with you rather than, the carrot and the stick, rather than the stick. No, we're going to fine you $10,000 a day if you do this. And then they, that's that adversarial approach. So the other approach is let's turn it around and make it something positive where the industry is going to help support us and fund us with the idea that we're not trying to get them in trouble. We're not trying to generate data from their waste that's going to take them to court. We're actually trying to find a way so that they can make more money and they can advertise being a better neighbor. For instance, example, Frulac, a company that just moved into town from Portugal. They make fruit that goes into, or they process the fruit that goes into Chobani, yogurt, the different kind of yogurt. So they came to me and said, hey, we're aware, and they're right here in Logan, we're aware that you make products out of waste. Can you do something with our waste that makes product? Now, the city says that we have to treat our waste to a certain standard. We realize that. But if you can make a product, in addition to that, where we can treat the waste and make a product, we're really interested in that. So they're funding a project right now. And I said, yes,
Wonderful.
Our whole goal is to make a product out of that resource. You don't have a waste, you have a resource that's out of
Wonderful.
place. So we're going to take that resource and grow. And West Tech, as he has up there, Central Valley, the U.S. Department of Energy, they're working with us for 4 years on U.S. Department of Energy gave us $2.4 million to look at doing the product out of wastewater, growing algae. And then from the algae making biofuels, biodiesel, biofertilizer, bioplastic. West Tech we teamed up with that industry to make the tank where we put the wrapper in the tank. And then we had PNNL, Pacific Northwest National Laboratories, that helped us do some microbiology and analysis of the biofilm. So they became very interested in the types of algae. That's a trickling filter, right, at Central Valley. Central Valley
showed
Water
on
Reclamation.
Henry,
Yeah. So there's your Central Valley. That's the largest water
That's Central
reclamation
Valley.
facility in the state of Utah. And you know what the management there wanted? They wanted to create products out of their waste. They said, can you help us make biofuels, bioplastics? And so they became the host for this project for $2.4 million. So we had the municipal industry, and then if this works there, it can be spread to all the other wastewater treatment plants in the country. And then we have West Tech, that's an environmental consulting firm that would be able to make this technology. Then we have Mississippi, Algix, that makes the shoes out of the algae. And then we had Utah State here also. And combining these together, this was a government academic industry collaboration, where the idea on this whole thing was to end up taking a waste and making products and treating the waste at the same time to prevent algae blooms from growing in receiving waters. So, in other words, we're not only removing the nutrients, but we're doing something with the nutrients in
Of
order
course.
to upcycle them into something that
Yeah,
we make.
that's
There's
awesome.
Central Valley Water Reclamation Facility. How's that? So we had a nice collaboration between government, industry, and academics that together we're publishing now that shows what you can do to team up the three elements. Oh,
Dr. Sims, how many students have you had? Have you mentored? Do you?
That's a really
it's
tough
like
one.
a estimate.
Yeah, somewhere around 25 PhD students and probably 45 to 50 master's students. Undergrads, I'm not sure, but that includes, that's 82 to now is 40 some years.
Yeah.
And so there's
Yeah.
a lot of, and if you have several projects that are multi-million, see that student right there, Jaden Storer. This is a good one right there.
Oh, yeah, Jaden.
That
I
you've
know
got
Jaden.
up. This is at Central Valley, and those. Here's a project. What he has, those two big tanks in the back. Those are anaerobic digesters. They take the solids.
Oh.
What happens is you bring food in, and the microorganisms grow, just like your pet when you feed it food. And then you can't put the pets out or the microorganisms in the stream. You have to separate the microorganisms and put the clean water out. And so what they do is they take the microorganisms that are growing and put them in those big tanks, shut off the air and no oxygen, and then they get anaerobic digestion. And what they do is they go on a diet, and then they eat themselves up and produce methane. And so that plant, half of the power of the plant is produced from methane. How's that? Then what they do with the solids, that it's called the buttons and bones. You can't convert all of it to CO2. So you have some calcium, magnesium left, but that becomes good fertilizer. But what they cannot treat is the water. They don't know what to do with the water in there. And that water, all these bugs have released all their internal, so it's high in nitrogen and phosphorus.
Yeah, I'm curious about this this process of cells eating themselves up to produce methane.
Yeah.
Could you describe a chemical pathway that
Yes.
that would
Sure will. Yes.
produce methane?
And so, yeah, keep that right there. That student took methane out of there that they're using for power. Now we'll
Yeah.
talk about how that changes. But that student took the methane out and found another organism. If you pass the methane through the organism, it will change it into a sun protectant called ectoin, the skin protectant.
Oh yeah, he was
That was
all
Jaden
about
Storer. So his master's project was to scale up this process, because it was only done in flasks around the country, but to take the methane, pass it through bacteria, and make ectoin out of it, which is $1,000 a kilogram. It's actually in creams and lotions that you put on your face. So he did that. Now, methane, when you put it in an organism and the organism starts to go on a diet, it will go what we call anaerobic. But as a result of that anaerobic process, you produce two major products. One is oxidized carbon, CO2. The other is the most reduced carbon. Because when you put it under anaerobic conditions, the redox goes down. There's no oxidation potential there. The oxidation goes down, and the organism ends up putting up CO2, which is a greenhouse gas, and methane, which is a greenhouse gas. So you end up getting the most oxidized carbon, the most reduced carbon due to anaerobic microbial combustion. So if you think about the organisms break things down, if you talk acetic acid, two carbons, acetic acid. And then what happens under anaerobic conditions is there's no oxygen, but you already have a COH. You already have the oxygen as part of acetic acid. Cleave it, just cut it in half. The other side is methane.
Oh, okay. So they produce acetic acid.
Yes. So on the biochemical pathways down, they produce acetic acid.
That makes sense.
Cleave
Just like us, right?
So they're called acetoclastic organisms. They break it in half, and you have the oxidized half and the reduced half. So you produce methane. So that's what we did. That's one of the products that came out of this project that was a spin-off. We weren't even trying to make ectoin, but he found a way to do it.
Yeah. Did he make some?
He did. He made some.
At this scale?
No, he made some at 10-liter scale. So the idea
Oh,
was
that's
if we could do,
huge.
yes. Huh?
How much?
So he
Can
did
you
it in
not
batch.
tell me?
No, yeah, we could.
Oh,
He
okay.
did it in batch, so he ended up producing more like milligrams amounts.
Okay.
Because just to prove we could do it,
Yeah.
right? It was
Yeah.
more of a proof of concept. You could scale
Yeah,
up to 10 liters and
yeah.
produce that.
You saying
Is that
you know?
project going anywhere?
There we
now,
go.
or-
He graduated, so I'll be looking for someone to continue that work. Very good, Rock. Right now, no, he got a job doing sustainable aviation fuel in Clean Fuel.
Oh, cool.
In Salt Lake City. So he just got that job last couple of months. This one here shows that chemistry we're talking about, where you get the air and the water, and then you make the algae, and it cleans up the air. So the idea we're using algae is because it captures the greenhouse gas, CO2, and it makes oxygen on the right-hand side. And you also get the algae biomass that becomes the source
Yep.
of bioplastics. So the idea is to take the
Stop.
water, which is waste, and then make it, upcycle it
Yep.
into that biomass. So if you start with that philosophy and then you look at ways to implement that with engineering tools, you start with the philosophy, we're going to upcycle. And we have to protect public health and the environment and industry. Now, how are we going to do that? How are we going to strategize? That's our problem. That's our challenge. Then you come up with using engineering tools and methods and, et cetera, in order to come up with ways to achieve those goals. Then when you get up and go to work, you're always trying to save the planet, which goes right back to 1970 on my first Earth Day. I always go back to that. We're going to save the world in 1970.
Awesome, Dr. Sims.
Okay, how's that, huh? And that's kind of a life story. You kind of got that. One other thing I could comment on is in this Superfund site. When I came here at USU, we did some work with a paper company. They had carcinogens in the soil because they dumped logs. They preserved telephone poles. They dumped the old poles in a bin in a pond, and then they contaminated the water. I have a slide of that where I'm with a graduate student, a PhD student at Libby, Montana. Carcinogens, no, not that one, but you'll see back a ways, and I'll go to the right there, I think maybe, right, a couple of, hit that one with, that's it. The next one to it, left, let's see, that one, yep. See that on the right? That's me. And we're at a hazardous waste site with carcinogens, and that's my PhD student, John Ginn. And we were hired by EPA to work with this company that contaminated their soil. We took the soil that was contaminated, that shut down the whole water supply. This is Libby, Montana. It shut down the entire water supply because the carcinogens leached into the ground. It wasn't the industry's fault. They didn't know at that time the technologies and the problems that were going to be created, but there was a problem created, so we went up there to solve the problem. And what we were working on is going to contaminated spots that were not so contaminated. You find microorganisms that can mutate, that can evolve. It's just like we do when we get the flu, right? And the one the next year is mutated. Well, these are mutated in order to break down carcinogens. They could actually degrade carcinogens, so we ended up trying to stimulate them by adding oxygen and tilling the soil. And out of this, we found three new microorganisms. These are mycobacteria. The mycobacteria are bacteria that cause tuberculosis. In this case, they were the first three environmental. The mycobacteria that cause tuberculosis inside the body, these were the first three found in the environment. So we had the Joint Genome Institute. Dr. Miller and I worked on this one. Dr. Miller helped me go to the Joint Genome Institute, and they did the genetic readout, and we found three microorganisms, brand new, environmental, that we could use as substitutes for the toxic, the pathogenic ones.
Great.
These are not pathogenic. So what we ended up doing is looking at different ways to impact or treat these organisms that would inhibit them from growing. And because they were new, I got to name them. And I named them after my family. So we have Mycobacterium JLS for Judith Larrabee Sims. That's official.
Nice.
We have Mycobacterium KMS for Kirsten Marie Sims, daughter. And we have Mycobacterium MCS for Matthew Charles Sims. So we found three.
Cool.
So I got to name all three after our kids and my wife. And they have linear plasmids. Most microorganisms have circular plasmids.
Oh, wow.
These have linear, which was brand new. And those plasmids were the ones responsible for degrading the polycyclic aromatic hydrocarbon. The carcinogens are polycyclic. They're benzene ring type and they cause, you know what, they're also in, these types of carcinogens are in cigarettes.
Oh.
And they also are people that have chimneys that burn wood, and the chimneys collect all this soot on the side. And that's a product of incomplete combustion, and that's why the chimneys catch on fire, but they're the same chemicals. So the chemicals that they use in these wood preservatives are similar to the ones in tobacco, but they cause carcinogens or cancer over a long period of time. But we found organisms that could degrade those environmental carcinogens.
Wonderful.
Yes. So then the idea is you could put vegetation on there. Once you degraded the organisms, you can put vegetation on, or you could put a building on there and not contaminate the groundwater, and that's called brownfields, where you use it. You can't bring it all the way back to eat the soil, but you can bring it back to where it won't cause cancer for people if you put a building on top of it. So
Yeah.
reusing that, right, kind of a good way to upcycle it. So the whole idea here was to try to upcycle this plant and deal with the carcinogen by trying to treat it using bioremediation. Right, so there's the soils. See, that's the farmer that we talk about. We start from farming, and then we branch out from there. So that's another story of a discovery that we did.
Oh, awesome.
Yeah. Contributing to public health.
Are there any more new discoveries in your lab?
So I think now what we're looking at now, so what's happened is Canada, there's an institute for the government of Canada called the International Institute for Sustainable Development. And what happened is they looked at our algae project at Central Valley, where we're treating the wastewater, growing algae, making biofuel. They came down and asked, let's see, that's that. You know what? That's that first one. Scale it up slide, where we have the big 3,000 gallon rotating algae biofilm
that's
reactor.
the rubber.
That's it. Yeah, that's the one. The one on the right here, the one that you have 2023 to 2025, that's the one. And so what we ended up doing is they came down and they said, can you grow algae for us in Canada? The people that we call, they're called First Nation. They're the native inhabitants, like we call here. The First Nation people would like to get help to go back to fish and rice. They want to do simple.
Where in Canada is this?
Ontario. So he came down and he said, can you grow, using that kind of thing, grow algae for us up in Canada in order to provide the algae that could feed fish and the algae that could fertilize rice.
Cool.
So what we're working on right now, discovery, they came down and said, can you apply this to agriculture? We've been applying it to waste to make products, but we don't eat it. So what they're saying is if we put this in a lake that just had some nitrogen and phosphorus, it's not contaminated with wastewater, but we could use those nutrients to make algae, and then we want to feed the algae to fish where the First Nation people could eat the fish, and then we want to use the algae for fertilizer to grow rice.
Cool.
What's interesting then from an engineering point of view, is that biofilm, that algae, has that struvite, that fertilizer, kind of buried in the matrix, and so they can't feed the fish ash. And the struvite is magnesium ammonium phosphate. It's ash. They can't feed that. The fish can't have a lot of ash. So what they said is, can you separate the struvite? Yeah, good. Can you separate the struvite from the algae so that we can feed just algae to the fish and the struvite to the rice? Now the algae is where we get our omega-3 fatty acids, because the algae what produces, so fish get their omega-3s from algae. So by feeding the fish algae, the fish then get omega-3s that makes them healthy, and then the struvite would be used to fertilize the rice. So this summer, I have 2 undergraduates working on projects of how to separate chemically the struvite from
the algae.
And this is for the International Institute for Sustainable Development.
Well, that's going to be hard.
International. Yeah.
Or maybe centrifuge.
Well, you know what? See, we're engineers. You're right. So now the idea is, okay, guys, go after that. But that's a very practical problem. And see that if you see the one on the lower left, right below your big one there, the greenhouse. Let's see, that's below. If you just go down, the big one I'm looking at.
Down.
The one on the
Left.
left bottom, big one. Big.
No. The one that you already had shown.
Yeah, so that's okay. Right there where you are. If you put that up there, and that one, that'll work.
Yeah.
Yeah. Separating the struvite from the algae. That's okay.
Thanks,
but that's
Henry.
where we're working on that project, is down there. So you ought to take a tour of that sometime. So the idea here is, if we do this, see, we're increasing. What are we doing? Public health, right? Because we're increasing the health of the the First Nation people.
Yeah.
We're taking care of the environment because we're making algae, and we're supporting industry. And in this case, it's a local industry where they want to grow fish and rice, cultivate rice. So you always look at those 3. Are we doing good for public health? Are we doing good for the environment? Are we doing good for industry? And this is a good project to do that. So we have this one. We have Upside Foods, as I mentioned, cellular agriculture, growing chicken cells. And again, the idea there is not to displace farmers. The idea is to help where countries are stressed by not enough water and stressed by not much land, so they can't grow lots of cattle in order to grow lots of meat.
Yeah,
so
it's creating products too.
Yeah. So the idea then is, again, improve public health where people that couldn't grow that meat have it, take care of the environment by using less water and less land, and then supporting an industry, which is cellular agriculture. So each project, you kind of run through the sieve, right? Does this help public health? Does this help the environment? Does this help industry?
Right.
And that's kind of the way I operate SWBEC. Is projects come in, I go, okay, can we do this? Can we screen through and have a chance to do these three things? And then students doing this learn skills that way. So this becomes hands-on teaching. Yeah, the hands-on teaching, and that's at Central Valley. They're big trickling filters. They move the water down from the top to the bottom, and it rolls over biofilms. In this case, it's bacteria to clean up the water. But in those windows, by happenstance, there's sunlight, and where there's sunlight and nutrients, there's algae. So we take the algae from there, and then we cultivate it. That's our seed. That's our starter culture for yogurt or bread. That's our starter culture for the rabbit, the rotating algae biofilm reactor. Yeah, and those are two students that are collecting algae to take it over maybe 100 feet and put it on that big tank that you saw, the rotating algae biofilm reactor. So the newest invention we have is the rotating algae biofilm reactor. And what's happened then is that the largest water reclamation organization in the country is called the Water Environment Federation, WEF. So WEF contacted me 2 years ago and asked if we could write the chapter. They do a manual of practice for engineers, manual practice on biofilms. They never had an algae biofilm. They have not had a chapter in that, but we are writing the first one. So in this book that will come out, there'll be a chapter on how to design, operate, monitor, implement algae biofilm reactors, and SWBEC is the author. And so I just finished, that's coming out this month, June.
Oh, wow.
It's that new. It's this new. So it is distributed to regular consulting engineers who are in the practice world. And what we're using...
So what is this? Sorry. This is a little product that you made?
This is, you want to go back to the scale it up one?
Or something that someone can use to...
Yeah, this is the
to show that
3,000 gallon.
this is what Rabbers will use.
Let's go to that big tank that says scale it up. That was one of your first slides that is down at Central Valley. That hit that one, and then hit that one next to it. Yeah. See that thing on the right?
Yeah.
Yeah, there it is. That is a rotating algae biofilm reactor.
Yes.
And so the idea then is how
you made one of those smaller.
Yeah, we have them all the way from 1 liter all the way up to that. And the manual, the only way, what we had to do for the manual is to do the scale up. Because the consultants want to build the bigger reactor.
Oh, okay. So the consulting firms want these to show to their clients.
Correct. And they want to know how
you provide them to them?
So what we do is we have this one, but in the chapter we tell them how to build one.
Oh, okay.
And how to operate it and how to monitor it. And
what
it might do. So the idea is they have a manual. It's kind of like Betty Crocker cooking. Number 1, number 2, number 3, and you build one of these, and then here's how you monitor it.
Oh.
So we gave them an instruction manual on how to design, build, test, because it's never been done before. So SWBEC, we had the opportunity to write the first one for this. They had one other book out 10 years ago, and they updated it this year, and even the one 10 years ago didn't have, because algae biofilms weren't known at that time. So we have been asked to write the first chapter for algae biofilms for the consulting world. So that's the application. See, that's the application side.
That's huge as well.
Yeah, getting it into industry. Yeah,
that's super huge.
Yeah. If you stick around long enough and you get good students.
Yeah.
And you really pound those students, they do it. They do it. They take it. They take with it. So the idea is, where I come from, is the idea of getting students and then having them take risks and fail forward. So come on up. You guys teach me. You guys throw stuff at me. It's the Socratic method, Okay, ask a question. Okay, throw stuff back. Now you guys go learn something and then teach me. So the idea is you're not a sage on the stage. You're a guide on the side. The idea is you work with your students as a guide, and then together you discover and make things going forward. And the idea is you encourage your students to try and fail and then come on back and say how they change that. So there's trust. Instead of worrying about failure, you go fail, and then come on back and say how you're going to change that so your chances are not failing next time. But share that with everybody so we all know, we all benefit by the failures, And then I call it failing forward.
Hmm.
So the whole idea is you progress by failure. Philosophy, right?
Wonderful, Dr. Sims.
Yeah, so what if you want to?
Oh,
put
yeah,
that
what
up
is
there,
that?
That
What is
is a
that you got
schematic
up
of
there?
how the Central Valley Water Reclamation Facility works. So what that does, what that big diagram there is it shows water that needs to be treated coming in on the left-hand side. So you can figure water's coming in, and then they have some of those settlers that look like where, just like a beaker in the lab, the sand, silt, and clay that gets in water settles out, and then the water that has dissolved nutrients in there, the water goes off the top, and that's the water that's got the dissolved nutrients that you have to clean up. And so you work that through bacteria and have them take out the organics. Then what's left is the inorganics, and you take that through the algae. And then the algae remove the inorganics, and then what's left is clean water that you put out. But in taking all that through the microbes, you increase the number of microbes, right? Because they transfer the food into them, they grow, and then you have to deal with those microbes. And so all that diagram is showing phases where the water comes in with solids and dissolved materials in there, and then they take the solids out, and then they move the water through, and they take out the organics with bacteria, and then they move it through algae to take out the nutrients, and then they can put it in a stream after they disinfect it. They can put it back in the stream, and it's cleaned. Basically, it's upcycled. But then all the bacteria and the algae they've generated have to go somewhere. So we take the algae and make these products, and the bacteria we put in an anaerobic digester and make methane and CO2.
Cool.
The CO2 can also be used to grow the algae, and the methane can be used to burn for power.
Wonderful.
And then the water left over, we can grow more algae. So the whole idea, notice it's not just recycling, but upcycling kind of thing.
Yeah. What advice would you give to somebody who's starting off, maybe in their undergraduate,
Yeah.
maybe even in BE?
Yeah.
What advice would you give to
Yep,
someone
one.
to have a successful career?
You bet. One, get involved in labs, and it doesn't make any difference what lab it is. Get into a lab. Get into a lab to get
agreed.
experience, helping, doing whatever it is. I mean, you can start washing dishes, and then you'll move up to another activity. But even washing dishes, learning how to wash out metals with an acid wash. I
Yeah.
mean, dishes, there's a lot to learn there. Learn solvents, and don't put a solvent in a plastic cup. That's a good idea. Don't get a plastic cup and pour gasoline in it. Things like that. So the idea, get involved your freshman year. As soon as you walk in the door, find some faculty member, volunteer. Don't even need pay. Just volunteer, because volunteer will give you skills, and those skills then will help you to maybe get more of an hourly pay later. 2, take chances. 3, fail forward. So get involved,
Cool.
Take chances, fail forward. If you go with those, then you won't be quite as constricted. The idea is to say that your coursework is important and your lab experience is also important. So you don't want to say, I'm only going to study and I'm not going to do laboratory work. The idea is to do some laboratory work while you're studying your basics. So find that balance, but don't give up on the lab or the experiential activities. Don't sacrifice that to do only the studies that you're doing.
Okay. Yeah, I think that would help. We got a Faculty Mentor of the Year.
Oh, yeah.
That Henry pulled up here. Oh, when was this? 2020, 2024? 2024.
Yeah.
Dr. Sims got Faculty Mentor of the Year. I think I just saw all his publications.
I think that was a university one. Oh, and then the
D.
Winthorn.
Winthorn Career Research Award.
Yeah. So we're talking about
That's
here is
good.
the emphasis in research and the emphasis in teaching. You don't have to sacrifice one for the other. So the
Right.
research award meant research career, and then the mentoring award was for mentoring in a teaching mode.
Yeah.
And what I'm saying here is a faculty member doesn't have to say, I'm a researcher, I don't teach, or I teach, I'm not a researcher. So the idea of taking those two and blending those so that you get the students involved in the research. And then they actually help you, and you help them. In other words, you don't have to look at, I'm either a teacher or a researcher. No. Again, that's like saying industry versus the environment. Come on. The idea here is we're engineers. We're smarter than that. So let's get the research and the mentoring or teaching together. And let's go in when we're lecturing and talk about the research we're doing. And then when we're doing research, let's get the students involved in doing the research, and that way they're getting mentoring. So again, these false dichotomies. Well, are you a researcher or a teacher? Which one? No. And a lot of people like to play that up and then give one up. But I think the responsibility, especially if you're in an R1 university like this, is to do both and figure out how to way to do it. And as engineers, we should do that. So that's part of the blending, so that you end up combining things to be more efficient, more effective in terms of time and energy kind of thing. You have a lot of energy in students. So the idea is, are you going to destroy that energy, or how are you going to use that energy? How are you going to utilize it? Not for yourself only, but for the students. So the deal here is the philosophy you come at the education system with is students have energy. How are you going to use that energy? Are you going to yell at them and they're going to be afraid and they're going to burn up their energy with stress? Or are you going to utilize the energy so that they can help themselves? And because you have more experience, your responsibility is to guide them in a way that they're learning. And they didn't plan to do it that way, but you're helping them because they couldn't have planned it that way. In other words, they just come in and go, what do I do? So you're trying to come up with strategies so that they can learn research while they're learning from coursework, and then put those together. And now you're doing research and mentoring at the same time.
And we noticed that you succeeded a lot on that, like working with the students, being a good advisor, mentor. But do you have any personal life experience that inspired you to be the person that you are today and to work with the students? Do you have any bad experience with the previous faculty, I don't know,
anything?
Life experience or good experience that inspired you to do the same with your students?
So I study my bosses. That's an excellent question. I study my supervisors as I've gone through everywhere from 1970 on. I study them in terms of looking at ethics, credibility, how much I trust them. Trust is huge. How much am I learning from them? Are they doing things to benefit others or just themselves? Where are they coming from? So the idea of having people that were inspirational all the way from high school. My physics teacher, I remember actually when I said, hey, I wanted to create life in a vessel. I wanted to put the chemicals in this tube and put an electric arc through it. It was the physics teacher that said, hey, Mr. Sims, good, we'll try it. We'll set it up in the lab. And so we set it up. He was very nice. I just remember this guy was very helpful. And then we put it in the lab, and over the weekend it blew up. Yeah, too much pressure. And when I came in Monday morning, he said, Mr. Sims, your tube, your globe blew up, and here's a little bit of the liquid that was left. He didn't yell at me and say, boy, you destroyed the clay. He just said, luckily nobody was hurt, and here it is. And that I still remember, like, wow, this was really cool. This guy was not mad at me, and I failed. So the idea of failing forward. And then, in college, the college teachers, the guy who had us sucking carbon monoxide, Mr. Ramsey, he was great. I really liked him. He was really good. He'd tell jokes in class, and he was very supportive. And when we did this experiment, he was always very supportive. So what happens in both of these? Trust, right? You start going, oh, part of this leadership inspiration is trust, building trust. And, so my advisor, as I mentioned, my PhD, my first advisor, Linda Little at Chapel Hill, master's, she was also really good. She came running down the hall one time. I'm doing research in wastewater treatment. She came down and said, hey, Mr. Sims, I found this article that's really going to help you. And so she gave me an article. She said, why don't you read that? And that'll be. She was helping me rather than just telling me, go find out this stuff and then report back to me. Like, wow. So it was more of a team where she still expected you to do stuff, but she was not sitting there saying, do everything. So I remember that. Like, hey, here's an article you should do. My PhD advisor was a really rough guy, but what we decided to do is I decided if he asked me to do something, I'm going to give him 10 times back. I'm going to bury him in the amount of stuff. And then he started respecting me, and then I respected him, and we ended up learning from each other. So that was a case of studying the person, and he wasn't just being mean to be mean, but he had really high standards, you'd call it. And once you come back and demonstrated that, he backed off. In fact, he turned in my dissertation for, the Outstanding Dissertation Award at North Carolina State, which I didn't get that year, but he ended up really being very supportive. But that was tough love. That was a tough love one. But the idea of studying and then studying your bosses, like in industry, Art Stern, who was the father of air pollution at Chapel Hill, and Dan Oken, who got his degree at Harvard, they were in charge of me when I was on the iPaid project, and they were supportive. They were, again, kind of tough, but integrity, right, and trust. I wasn't afraid of being fired. They were, if I did things wrong, which I did, they were going to yell at me. But it was in a sense of, come on, get this thing. Do this thing right. My first job in iPaid, I made up a flyer and I spelled everything wrong. And then he called me in Art Stern and said, "This is all wrong. You got to do this again." And I said, "Whoa, I'm really sorry. I've learned a lesson." He said, "Well, don't do it again." But that was building. So failing forward. I mean, heck, So
Failing forward.
What that question idea is, I study people. I study my supervisors in terms of leadership. Trust is a big one, and how they treat other people is huge. Didn't meet some people in the industry, didn't like the way they treated people. It was much more cold kind of thing, and more of self-concern rather than concern for the good of the group. Teamwork, I always look for teamwork. Were they interested in a team kind of development? And the dean, when I came in, Scott Hinton, was that kind of guy. He was a real visionary, a real leader. So studying how he thinks and how he approaches things and how he categorizes and how he builds teams. So I study people that are in charge of me in order to learn this way, in order to learn what I'm, in order to impact how I look at things. But I think ethics and trust are huge, and teamwork, because that's the way you're going to do it. Unless they just, you're the kind of person in a room that you want to be by yourself and you generate. But most people have to work in a team. And so earning that respect and trust is critical. And then watching how team leaders do that. Very much my hero is Abraham Lincoln for leadership. And the book, Team of Rivals, that's my Bible. The movie I've seen about a dozen times. The book I'm reading again for like the third time. But studying Team of Rivals, where you actually brought people on that were critical of you, that criticized you, I think is really, really good. So when people criticized me, I would go back and look for what I could get out of it rather than why I was so mad at the person. Initially, yeah, I mean, God, they're yelling at you. But the idea of to go back and analyze, all right, where are points I can learn to change my behavior. And Lincoln is the star doing that. So he's really my hero.
So could you say that times from before were different than today? Or do you think that in terms of interaction with the students and mentors, do you think that today we have the more lack of empathy, or before we have lack of empathy? Because some people say, oh, in the older days it was much more rough, people was more tough, and some other people say, no, today is so much more rough, there was not much empathy.
Yes.
But in your opinion, what do you think? Do you think it's the same? Is all depending on the person, or do you think is today it got better, or before it was better?
Yeah, okay, good point. I think it has changed. And when I grew up coming through all of this in grade school, high school, there was more distance between the teacher and the student. Just more distance, not because of anything where they had an attitude that they weren't going to get involved, but we just didn't know better. You went in and took notes and you took tests, and teachers kind of graded the test, and then you went on to the next one. And once in a while you'd hit somebody who was more personal or less personal. But the whole idea was we're educating a group of people that are going to get good jobs, and that's kind of our function right now. There wasn't an awareness of any interpersonal interactions or any of that. It wasn't that they were asympathetic, it's just we had a job to do and you were to study and they were to teach. And so they weren't mean, but they weren't interested in you as a person, let's say, most. There were exceptions, but it was much more of almost not like a factory. Go in, take your notes, pass, you get an A, and then you go to the next one, and you go to the But today today it's different. Today there's a lot more interest in teamwork and communication and working together. And I think today because of social media, and all the other ways we have to communicate, it's worse and better in terms of the stresses that students deal. I mean, it was no, if you think no computer, no cell phone, no TikTok, what did you have to do? You studied, you took tests, you didn't travel as much like today, so you were with your family. There was less of that interaction. So in other words, it was more like you were doing individual ping pong balls, right? But today, we're all tied in a web. Today, everybody's tied into everything, whether you like it or not. Social media, computers, everything is coming at you. The energy is hitting everybody. So in that sense, there's good stuff that comes out of that because we are more in tune with each other. The bad thing is that sometimes there's so much coming in that we're not able to deal with it very well. We don't have the tools because in school, we don't have courses in engineering of how to work in interpersonal relation. We'll get there. But the idea is we don't have as much of that as we need. And so therefore the students don't have skills where they're being to handle the stresses they're being hit with, which means that there's more frustration, I see, and there's more stress the students are having to deal with. And so it has changed, but the faculty don't know what to do because they haven't been trained that way. The faculty, we're not trained as psychologists or social workers when students come in, and so where do we go? I don't know what to do because I don't have any of these skills. And then we're told, well, you can tell the student, well, there's these support services, but I still don't have any skill. I haven't been trained in skills in psychology to deal with this. And so a lot of the problem today is that the generation coming through needs some kind of help that the faculty have not been trained to participate in. And therefore, there's this disconnect kind of thing.
And just to conclude the session,
Yes.
You mentioned about like psychology and how to work with that as a mentor. And we know that today's easy to deal more with mental health issues, including in school. So what kind of tools that you use to manage your own mental health and to support your students? Because we do know that you work with Aikido.
Yeah.
You are an instructor. So what kind of a device or kind of tool recommendation that you would give to other students that you do to yourself or you would recommend to someone else?
Yeah, really good. So following up, right, I teach a martial art called Aikido, which translates way to harmonize with energy. And so the idea in Aikido, physically, we don't punch or kick, but we deal with the energy of an attack and not to hurt the person, but to control the person. So the idea in Aikido is that you look for energy. You're dealing with energy, and the energy is neutral. There might be an ill will behind it or a good will, but you're not dealing with that. You're dealing with the energy, and you're coming from the point of view of, I'm not inflicting injury, but what I am trying not to do is injure the person who's attacking. So what that translates to, 20 years ago, I teach it at the Hyper. And so at the Hyper, it was a self-defense course. If somebody punches you, how do you come back without a punch, but to control them, not to hurt them, but to immobilize or keep them away so that you're trying not to hurt them, but you're not hurting yourself. Over the 20 years, it is now a stress management course. So what I've seen now is the course is translated into, look, the punch or a kick is kind of a, it's like a comparison, simile, metaphor, a metaphor. Let's call it a metaphor. So the idea is that's a metaphor, and you have energy coming at you. And then I start telling the kids, when you have this energy coming at you, people, weather, advisors, family, what kind of tools do you have to deal with that? When you get that, we're animals, right? And so the adrenaline starts, and you do the fight or flight or back. So teaching the students when energy comes in and hits you, what do you do with it? And so what I'm trying to get them to do is take it in and don't do anything with it. Just let it settle. And then you're not an animal. An animal will react. What I'm teaching the kids to do is respond, and there's a difference. Reaction is what an animal does. Respond is what a human should do. Animals react. Humans, we're better than animals in the sense that we can be trained to respond. So your response first is nothing. So you take the energy in, and then you make decisions about how you're going to respond. You're in charge of yourself. So self-control becomes a huge part of the course, where I tell students, if you can't control yourself, you can't control somebody else. I can teach you in 3 minutes how to hurt somebody, but you're going to be out of control. It is not a big deal to teach somebody how to fight back and hurt, but it's much more difficult if you're going to try and deal with the person and not hurt them. So that takes, as we're talking about, that takes training, it takes philosophy, it takes practice of receiving energy and then deciding what you're going to do with that energy to give back. So verbally, how you respond to criticism, physically, something come at you, how you respond to criticism. Most of it is that psychology where we've got all this stuff coming in and we have, hormones. Jeez. So the kids are filled, and I go, you're not supposed to be on drugs, but you are. They're called hormones. So how the heck are you dealing with those hormones? You guys, we don't really have tools to say when you're hit with that, that's real. That's not something that's not real. Now, what are you going to do with it? So as a human being, now how are you going to respond? And so in the idea in Aikido is you have this energy coming in and then you figure out how to respond in a nonviolent way that it keeps the door open for the attacker, but also helps you grow. And so your response, if it's energy, instead of that person doesn't like me, I'm going to punch him back. No, the person that attacked is out of control. So are you going to get on the same thing and be out of control? No. So the idea is you have to be careful not to take it personally, but look at it from an engineering point of view. That's why I love Aikido. It's a good engine. I'm looking at energy. I'm looking at energy coming in. And so how am I going to deal with the energy rather than I hate this guy because, really. So when that comes in, your first reaction, anger or happy, I tell people, look at the buttons on you. And where people are afraid to look at the buttons on them, they want to hide behind that. And I go, no, it's real. But that doesn't mean you have to react to that. You're a human being. So take the button in and feel it, and then you make a decision on how you're going to respond. My course has changed more to stresses coming in from outside world and how you decide how you're going to respond to those and teaching tools to do that. Thank you for that criticism. Okay, I get what you mean. I might not agree with you, but I understand where you're coming. In other words, repeat. You start these things where you learn to acknowledge, but that doesn't mean accept.
Do you have any good quotes from Aikido to finish us off here?
Oh, that's a really good. So true victory is self-victory. So the founder of Aikido said, don't try to beat anybody else. So true victory is self-victory. We have enough to work on for ourselves, rather than I'm going to spend my time trying to beat somebody else. So he calls it true victory is self-victory. Work on yourself. Yeah. How's that?
Great.
Good
Sounds
question.
Great.
So it's a good blend. Engineering is a dang good. I found it when I was doing my second master's degree, going crazy, right? With I need some release area. And Judy said there's a self-defense course for non-aggressive people, and I went, that sounds crazy because I took a course in jiu-jitsu undergrad. I thought that was ridiculous, so I went and watched it, and then I fell in love with it. So learning Aikido, and then I started to see how you're dealing with physical energy, and then how you metaphor that into now psychological energy. But it's a good workout. You go work up a sweat. He's done this with us. You go work up a sweat, get a good workout, you feel more energy. That's the other thing that got me through my PhD. I would go do Aikido, and then I could go home and focus on math. I was minoring in math, and I could focus on advanced calculus until 11. I could go to bed and sleep 6 good hours. Yep. But if I didn't go, if I said, I'm tired tonight, I don't want to go to Aikido, and I felt crappy.
Wait, I think I heard Henry did Aikido with you?
Yeah, Henry's coming to Aikido now. How about that? We got Henry doing some Aikido.
True victory, self-victory.
It's the martial art for engineers.
Oh, great.
Oh, great.
Well, okay, guys. I think
right,
that's all the time we had. So thanks, everybody, for joining the Biological Engineering Podcast. And thank you, Dr. Sims.
Thank you very much, Kyle. Yeah,
being on with us.
Great opportunity.
Shout outs to Rock.
Yeah, thanks, Rock. There you go, guys.
And
Thank
shout outs
you
to
so
Henry.
much. Yeah.
Henry.
Thanks, Kyle.
You're the man.
Thank you, Henry.
Okay. See you, everybody.